Students, in our last class we had started to discuss about linear vector spaces. We had seen what a group means. Now let's go deeper into the topic, right? And let's try to understand what fields mean. Okay, first look at the definition. A field is a set F with two binary operations, addition, which is defined by F plus. If A and B are two elements, it is nothing but A plus B, and multiplication, which is defined by A dot B, or AB rather. Right? So field consists of its elements of set F and two binary operations, addition and multiplication. Now the conditions that needs to be satisfied are the elements, that is the set F, be an abelian group under addition. If 0 denotes the additive inverse, this point 1, point 2. If 0 denotes the additive identity of F, then the set, say we denoted F star is equal to F minus 0, is an abelian group under multiplication. And the third point is addition and multiplication are related by distributive law. Right? So these are the three axioms which needs to be satisfied by a set F and two binary operations, addition and multiplication, to be called as a field, right? So now let's try to elaborate these. Now to fulfill, so I would like to recall the terms that we have already come across. First is binary operation. By binary operation, what we mean, when it acts on the elements of the set, we get another element of the same set. That means if we add two elements of the set F, since addition is a binary operation, the value obtained A plus B also needs to be present in the same set, right? Similarly, since multiplication is a binary operation, on multiplying two elements of a field, the third element that we get should also belong to the same field, right? So these conditions needs to be fulfilled. Secondly, F be an abelian group under addition. So by definition, say if A, B, C, these belong to the field F, by abelian group these conditions needs to be fulfilled. First is the elements need to commute, that is A plus B should be equal to B plus A. B, they need to be associative, that is A plus B plus C is equal to A plus B plus C. These needs to be fulfilled. There has to be an additive identity such that on performing addition with an additive identity we get the initial element back. And the third criteria is for all the elements of the field there needs to be an additive inverse, so that on adding both we get the additive identity back. So these four conditions needs to be fulfilled for the elements of F to be called an abelian group under addition, right? Also the set of elements devoid of the additive identity should form a multiplicative group under addition, an abelian group under multiplication. So for these to be true, these conditions needs to be fulfilled. that is AB is equal to BA, that is they need to commute, they need to be associative, right? There needs to be a multiplicative identity such that when you perform the operation of multiplication with the identity and the element, you get the original element back. And a multiplicative inverse needs to exist such that on performing multiplication we get the multiplicative identity back, right? So even these elements need to be present in the same set if these conditions satisfy, and also the addition and distribution are related by distributive law. That means the elements must satisfy relation of this sort, that is distributive. Addition and multiplication are connected by distributive law. So all these conditions needs to be satisfied by the elements and the binary operations addition and multiplication so that they can be called a field, right? In terms of conditions, in terms of the number of conditions you need to remember, it might appear to be very complex indeed, but it is easier to remember because the examples, the most common examples of fields are real numbers. Real numbers. If you check by yourself, real numbers do follow all these axioms. So real numbers form the most common example of fields, right? The other fields are formed by complex numbers, rational numbers, and so on. But we will mainly be dealing with real numbers. Please check by yourself that real numbers and complex numbers do form a field because they satisfy all these axioms, right? Okay, now let's try to prove few identities and few equations. Question 1. Prove that for fields A0 is equal to 0, where A and 0 belongs to a field F, such that 0 is the additive identity. Now looking at the question, it might appear very silly to you because multiplying anything by a 0 means a 0, but the question does not mean a 0. Okay, whenever you see problems like this, now you have to treat 0 as the additive identity, right? So the question basically means multiplying any element of the set F or field F with the additive identity gives you the additive identity. This is what you need to prove. So do not treat this 0 as a normal 0, rather treat this as an additive identity, right? So we have to use the axioms of a field, since it has already been said that A and 0 belong to field and 0 is additive identity. So we will be using the axioms of field to finally prove this, right? We will be treating 0 as a additive identity and finally we will prove this. So let's see how we can do it. Say we write a 0. Now 0 is nothing but the additive identity. So this can be written as A0 plus minus A0. Now how can we write this? We have written this using the fact that the element plus its inverse, additive inverse, gives me the additive identity. So I have used the property of element plus its inverse gives me the additive identity. This property has been used. Please write in words. I've just written in short. So now we want to expand this more because our goal is that we're going to prove A0 is equal to 0. So what we do is A0 plus 0 plus minus A0. we have used the property that any element plus the additive identity is equal to the element itself. That means 0 plus a 0 will obviously be equal to 0, right? So this property has been used over here. Now, since the elements of the field are distributive over multiplication and addition, it can be written as A0 plus A0 plus a minus A0, where the distributive property has been used, distributive under addition. Now we also know addition is associative, so we can associate these two terms, right? So this comes from the associative property of field. Now A0 plus a minus A0, this is nothing but the element plus its additive inverse, so this will obviously become 0. That means we are left out with A0 plus 0, which finally gives me A0 is equal to 0, right? So we have finally proved that multiplying any element by the additive identity gives me the additive identity by using the axioms of fields, right? Let's look into another problem. Say for example, we want to okay, question: if f be a field such that A and B belong to the field F, satisfying AB is equal to 0, then show that either A is equal to 0 or B is equal to 0, right? Again, from normal algebraic knowledge of algebraic equations, we obviously know one has to be 0, but like I said, we won't be treating 0 like that. We will be treating it as the additive identity, right? So we have to show either A has to be 0 or B has to be 0 for this equation to work, right? So let's consider A not equal to 0. So we have to prove that B is 0, right? So we start with a 0 and A inverse, say we are writing 0 as this. Obviously this can be written since A inverse is nothing but the multiplicative inverse of A. Okay, we can write 0 is equal to A inverse 0 just by using the property we have just now proved, right? We have just now proved that A0 is equal to 0. So using that property, we can write 0 is equal to A prime 0, right? Now, where A prime is nothing but the multiplicative inverse of A. Now A inverse, and over here we have AB equal to 0, so we can substitute 0 by AB. Now since it is associative, we can write A inverse AB. Since A inverse is the we have already written it as a multiplicative inverse of A, so A inverse A is nothing but 1 into B, so 0 is equal to B since 1 is the multiplicative identity. So we can easily prove that if A not equal to 0, B equal to 0. Similarly, if it is the same, if B not equal to 0, A becomes 0, and it's the same thing, right? So now for your homework, I will just give you a hint. You will obviously do it. Few problems have been given in your PDF, so do try to solve them. I would just like to hint about a problem that has already been given. Show that the additive and multiplicative inverse are unique for each element, right? Show that the additive and multiplicative inverse are unique for each element. So I won't solve it for you, but I'll give you a hint. Let's consider that A, B, C, these are elements of a field, right? Now additive inverse, by additive inverse, what do we mean? If we consider B is the additive inverse of A, let's consider B is additive inverse of A. If that is the case, that means A plus B is equal to 0, right? Because any element plus its additive inverse gives you the additive identity. Similarly, if C is the multiplicative inverse of A, that means A dot C is 1, because since we are considering C to be the multiplicative inverse of A, so A multiplied by the multiplicative inverse will give me the multiplicative identity, right? So these are the two equations, and now you need to solve them just like you have solved for a group. You will consider B as additive inverse, and you will consider another equation A plus B prime as additive inverse, and finally we will prove B and B prime are equal. Similarly, for multiplicative inverse also, you will start by saying let C and C prime be the two different multiplicative inverse, and then we will finally prove that C and C prime has to be same, like we have already proved for groups, right? Okay, and the last problem that I would like to like you all to know, and I find it really, it's quite interesting. Show that in a field the additive identity cannot have a multiplicative inverse, right? Show that in a field the additive identity cannot have a multiplicative inverse, right? Now let 0 be the additive identity, right? Now if 0 has to have a multiplicative inverse, that means, say let A be the multiplicative inverse of 0. Let's consider A is a multiplicative inverse of 0. That means what needs to be proved? 0 multiplied by A, that is 0 multiplied by its multiplicative inverse, should give me the multiplicative identity. That means if this equation would have been satisfied, the additive identity would have a multiplicative inverse. This equation needs to be satisfied, but like we know, this is impossible because just now we have proved that 0A is equal to 0. So this equation immediately tells us that this cannot prevail, and hence the multiplicative identity the additive identity cannot have a multiplicative inverse, right? So this problem has already been solved just that due to the terminology I wanted to show you this, that it's beautiful to see that the additive identity cannot have a multiplicative inverse, and it has already been proved, right? Okay, so I think that should be enough for you to know about fields. So now let's try to at least start by the definition of linear vector spaces, and I don't think too much progress can be done today, but let's at least define what a vector space is. Okay, so vector space. So now we are formally entering into the broad topic. Okay, so we will mainly be dealing with real vector spaces, so I'm just writing mainly for real vector spaces. A real vector space is a collection V of vectors together with two binary operations, addition of vectors and scalar multiplication multiplication of vectors by a real number. Over here we are using real numbers because we are defining real vector space satisfying the following axioms. Okay, before I define the axioms, I want to tell you real vector space is an abstract and a generalized concept. Anything, any element, any substance which follows the axioms will be called a vector space, right? So the requirement of a vector space is it needs to have a collection of elements, or which we call as vectors, and two binary operations, addition and multiplication, associated with the vectors, which needs to satisfy few axioms. Anything that satisfies the axioms will be called as a vector space, right? So let's see what the axioms are. First, let's define. Let the vectors be given by v1, v2, v3, which belong to which are the vectors of the vector space V, right? And let alpha 1, alpha 2 be the scalars, or rather, in case of real vector space, the scalars which are real numbers, right? So the axioms which needs to be fulfilled are first A1, addition is commutative. Why addition is commutative? We mean v1 plus v2 has to be v2 plus v1, right? The second condition is A2, addition is associative. By associative, we mean v1 plus v2 plus a v3 is equal to v1 plus bracket v2 plus a v3, right? So for vectors, addition is associative. The third condition is there exists a zero vector, or rather the identity vector, such that v plus 0 is equal to v, right? So this 0 must exist in the vector space. The 0 must exist in the vector space, so that on performing addition with another vector we get the original vector back. Also, the additive inverse for each element must exist, that is v plus a minus v must always be there, such that we get the additive identity back. We can summarize all these four properties in a single line, that is the elements need to be an abelian group under addition, right? Now the fifth property is now it is the property of a scalar. Scalar multiplication is consistent with regular multiplication. Scalar multiplication is consistent with regular multiplication. That means we can write if alpha 1 alpha 2 v is equal to nothing but alpha 1 alpha 2 out of v, right? So multiplication is like normal multiplication that we perform. Our sixth axiom is addition of scalars is distributive, right? That means alpha 1 plus alpha 2 will multiplied by a vector, it will distribute it among the vectors. The scalars will distribute itself, right? So addition of scalars is distributive. The seventh properties, addition of vectors is also distributive. That means v1 plus v2 is equal to alpha v1 plus alpha v2. And the eighth property is the scalar 1 must exist such that the scalar multiplied by the vector gives me the vector back, right? This one is a scalar. So the scalar 1 must exist such that on multiplying the 1 with the vector, we get the vector back. So these properties needs to be fulfilled for the elements or the collection of vectors along with two binary operations, addition and multiplication, to be called as a vector space, right? you can obviously summarize this that the elements need to be form a abelian group under addition. The scalar multiplication has to behave like normal multiplication. Addition of scalars and vectors need to distribute among themselves, and the scalar one must exist, right? So these are the conditions which you need to remember. So now let's have a look on I would just like to tell you one more thing. We are considering real vector spaces, but a vector space can be a generalized one. It need not necessarily be a real vector space. So at that time, the scalars that we have already mentioned over here will belong to any field, right? So if you want to define a generalized vector space, you just need to replace the term real numbers by scalars from a field. Okay, so that field can be a field of complex numbers or rational numbers or whatever it is, but we will mainly be dealing with real numbers, right? So now, like we have always worked in the two-dimensional space or the n-dimensional coordinate space, so now let's see that that is nothing but a case of a vector. That means the generalized vector space, when we put the conditions, we see that actually the two-dimensional coordinate space is a vector space. We'll prove that, right? So let's see. So now our space is a two-dimensional coordinate space, and we will prove that it is a vector space, right? So from the generalized concept, now we are coming to the precise two-dimensional coordinate space, right? So to start with, before starting, I would like to tell you the notation that I'm going to use. We will be representing vectors by an n tuple of a n-dimensional vector by an n tuple of ordered coordinates, right? a1, a2, dot dot dot, an. So this is how we will be representing vectors. This is nothing but a1 I cap plus a2 whatever it is, and it continues, right? So these are nothing but the coordinates. Okay, so now let's try to see that actually the vectors of the two-dimensional coordinate space form a vector space. So one by one we will just prove the axioms, right? So let the vectors of two-dimensional coordinate space be written as we'll write it as xy, right? This can obviously be extended to n dimensions. We are just doing it for 2 dimensions. Okay, and scalar multiplication, let the vectors of R2 be defined by this, and scalar multiplication, is it visible? Just a second. Scalar multiplication by alpha x comma y is equal to alpha x comma alpha y, right? I don't think this is nothing but you all know this. Say it is a vector scalar 5 by whatever it is, x I cap plus y j cap. So it is nothing but 5x I cap plus 5y j cap. So that is what I have written over here, right? Just in a different notation. Okay, so now we will prove the axioms. The first axiom is they need to commute, right? So there is nothing to prove over here. We know that x1 and y1 plus x2 comma y2, they commute, right? Because this is nothing but this y1 plus y2, and it is nothing but x2 comma x2 plus x1 comma y1, right? These are just in a notation which is convenient for us to write. You can obviously see it if you are comfortable. You can expand it and write if you want, but these notations are helpful to write such equations, right? Okay, now the axiom 2 is, so we have already proved that the vectors of the two-dimensional space commute. Now we need to prove their associative, right? So if we have vectors x2 comma y2 plus x3 comma y3 is equal to x1 comma x2. When we add vectors, this is what we get, right? y1 plus a y2 plus y3, and it is nothing but x1 comma y1 plus x2 comma y2 plus x3 comma y3, right? We write it this way or that way, this is the result we will get. So obviously they're associative, that is the vectors in two-dimensional space are associative. Now we need to see if the additive identity exists, and obviously we have a vector 0 0 in the two-dimensional space, such that if we add a vector with 0 comma 0, we will get the initial vector back. That means the additive identity do exist. Then we have to find whether the additive inverse exists or not for each vector, and even that exists because minus x comma minus y, this vector is very much a two-dimensional vector, and when you add these two vectors we get the additive identity back, right? So the additive inverse do exist. That means already the first four conditions have been proved, that is the elements form abelian group under addition. Now we have to see the rules of multiplication. Alpha 1 alpha 2 x comma y, we have to show that this multiplication is same as normal multiplication, and this is nothing but alpha 1 alpha 2 x comma alpha 1 alpha 2 y, right, is equal to alpha 1 alpha 2, we can take that common, x comma y. That means it is getting multiplied like normal multiplication. The second is it is distributive over the scalar addition, right? So alpha 1 plus alpha 2 x comma y is equal to, this is nothing but alpha 1 plus alpha 2 x comma alpha 1 plus alpha 2 y is equal to alpha 1 x comma y plus alpha 2 x comma y. So obviously the addition of scalars is distributive, right? M3, the addition of vectors needs to distribute, so that means alpha x1 comma y1 plus x2 comma y2, this is nothing but we can write it as alpha x1 plus x2 plus alpha y, this is not a plus, this line is, this can be written as alpha x1 plus x2 comma alpha y1 plus y2, right, is equal to, the alpha can be taken outside, and x1 comma y1 plus alpha x2 comma y2, right? So even the addition of vectors are distributive. And the last is obviously the scalar 1 exists such that which when multiplied to x comma y gives me x comma y. So since all the axioms gets fulfilled by the vectors of two-dimensional vector space, we can conclude that the two-dimensional vectors of a two-dimensional vector space do form a the two-dimensional coordinate space do form a vector space, right? Now for your assignment, I have given a question in your PDF, so please solve it. That is, you need to show that the matrices n matrices do form a vector space, right? So try to show that, and that's all for today's class. Thank you.